In this video, we're going to focus on carbon dioxide transport. All right, we're going to use yellow here because why not? Okay, in order to understand carbon dioxide transport, you need to remember this equation. CO2, so carbon dioxide plus water, turns into carbonic acid. Okay, and remember, this is with the help of carbonic anhydrase. And what's really interesting about carbonic anhydrase is it helps with the reaction of taking carbon dioxide and water and creating carbonic acid, but it also helps with taking carbonic acid and turning it back into carbon dioxide and water. Okay, and then what can happen is that carbonic acid can turn into bicarbonate as well as, hydrogen ion plus bicarbonate. Okay, so let's start off in the tissues here. Okay, so in the tissues, the tissues produce CO2. Okay, the CO2 will diffuse into the plasma. Okay, once this happens, one of a few things will happen. First, CO2 will just stay in the plasma. Okay, nothing happens, and that's great. It's just in the plasma, it's going to stay there. All is well in the world. Okay, the second thing that will happen is CO2 will diffuse onto the red blood cell, a red blood cell. Okay, and from here, a couple of different things can happen. Okay, and I'm going to change the colors here. Okay, so first, CO2 can bind to hemoglobin. Trying to make up words here. Can bind to hemoglobin. Okay, so hemoglobin is HGB, so this is that carb amino hemoglobin. And remember, when this happens, that means there's decreased oxygen affinity. Okay, because the carbon dioxide makes it more difficult for oxygen to bind to hemoglobin. Okay, the next thing that can happen is CO2 goes through this reaction. So CO2 plus water ultimately forms, and I'm skipping the carbonic acid step, hydrogen ion plus bicarb. Okay, and from here, something happens with each of these. Okay, hemoglobin will combine with hydrogen ion. This also decreases oxygen affinity. This is a right shift. Okay, this is a buffer, and we'll talk about that more later on in the semester. Okay, but now we've got this bicarbonate, and we don't want that bicarbonate just staying there, and so then what happens is this diffuses, this is swapped into the plasma for a chloride ion. Notice they each have a charge of -1. And so what happens is we get bicarbonate off of the red blood cell and into the plasma where it can be transported more easily. But in order for this to happen, we have to maintain the charge. And so we get rid of we take a bicarbonate off and we bring a chloride on. Okay? And so as a result, notice that we've got 3 different ways where we're transporting carbon dioxide. So we've got here in the plasma, we've got here bound to hemoglobin, and then we've got here in the plasma. Okay, it's not it's not being transported as chloride. We're just swapping out the chloride, but the bicarbonate is in the plasma. Okay. All right. So now, what happens when we get to the lungs? Hot pink seems like a nice color. My daughter would agree. So we're now in the lungs. Okay, so let's go through each of those 3 ways. So we've got first the CO2 in the plasma. It diffuses into the alveoli. That's easy. Okay. All right. So then you've got the HbCO2, that's that carbaminohemoglobin. Well, then that becomes CO2 plus hemoglobin. And so then the CO2 diffuses into the plasma. And guess what? It also then diffuses into the alveoli. All right. So then we've got the bicarbonate. So the bicarbonate in the plasma swapped on to the red blood cell for a chloride ion. That's that chloride ion shift again. Okay. So now bicarbonate combines with hydrogen ion. Remember, so that hydrogen ion that was bound to hemoglobin right here. So now that hydrogen ion separates. And so then what happens is we go through that reaction, we go through carbonic acid, but eventually what happens, again, I'm skipping that middle step, we have carbon dioxide and water. And guess what? This carbon dioxide right here diffuses into the plasma, where it then diffuses into the alveoli. Okay? That is carbon dioxide transport at its most simple. And so when we get in the lungs, when we get into the lungs, all of these things, and not all of these things, let me be a little more clear. So steps 2 and 3, we'll write it down here. So steps 2 and 3, these lead to a left shift of the oxyhemoglobin curve. Okay. Whereas up here, and I'm just going to star them, and I'll put up orange, okay? So this one and this one, okay? So this means in the tissues, we actually have a right shift, okay? But that's actually a really good thing, because in our tissues, we want to get rid of oxygen. We want to get that into the tissues, okay? Whereas in our lungs, we want to pick up oxygen. So the left shift in the lungs is really good because it makes it easier for oxygen to bind.